Hi, in this video we are going to talk about bitwise operators in C++. Please note that there are total 6 bitwise operators in C++. We are going to talk about first 3 in this video and then next 3 in the next video. Now, what do we mean by a bitwise operator? There are arithmetic operators that do addition, subtraction, multiplication, division. There are logical operators that return values like true and false. Right? They always deal with true and false. They are used inside the conditional statements mostly, like if, while, for. Bitwise operators, they work on binary representation of numbers. They mainly operate on individual bits of the number that you pass to these operators. Let us begin bitwise operators with these 3 operators. First operator is bitwise AND. So what bitwise AND operator does, it does bitwise AND of binary representation of 2 numbers. So you must have studied AND gate, right? An AND gate produces an output as 1 if both inputs are 1. In all other 3 cases, it produces the output as 0. If input is 1, 0, then also 0. If 0, 1, then also 0. If both zeros, then also 0. It produces output 1 only when both the inputs are 1. Bitwise OR, it produces the output as 1 when any of the inputs are 1, right? For example, if your input is 1, 1, it's going to produce 1. If input is 0, 1, then also it's going to produce 1. If 1, 0, then also it's going to produce 1. In case of 1, 0, 0, it's going to produce 0. So bitwise OR produces 1 in 3 cases and 0 in 1 case. It's kind of opposite of bitwise AND, which produces 1 only in 1 case and 0 in 3 cases. Next operator is bitwise XOR. Bitwise XOR is interesting. It produces output as 1 when 2 input bits are different. For 0, 1, it produces 1. For 1, 0, it also produces 1. For other cases like 0, 0 and 1, 1, it produces the output as 0 because both the bits are same in both cases 0, 0 and 1, 1. Let us now begin with first bitwise operator, bitwise AND. Let's see this example. We have input x as 3 and y as 6. And when we print x, x and y, we get the output as 2. Right? The output of first line is 2. Let's see how do we get this output. So binary representation of 3 is this. We have first 30 bits as 0 and then 2 bits as 1. Considering that integers are represented using 32 bits. If they are represented using 64 bits, then first 62 bits will be 0 and last 2 bits will be 1. Binary representation of y, which is 6, is going to have 1, 1, 0 at the end, last 3 bits. And if integers are represented using 32 bits, then first 29 bits are going to be 0. Please note that number of bits required to represent an integer is not standardized. It's not mentioned in the C++ standard. Compilers are free to choose any size. Some compilers have integer size as 32 bits. Some compilers have 64 bits. Some old compilers even have 16 bits. So that is why I've used ... So these first bits might be 30 bits or they might be 62 bits. Similarly here, these zeros might be 29 bits or 61 bits if 64-bit representation is used. Now if we do bitwise AND of these two, please remember the rule of bitwise AND. It produces 1 only when both input are 1. So we have 1, 0 different, so we have output is 0. 1, 1 same, and both are 1, so our output is 1. 0, 1, 0, 0, 0, 0. And all the previous bits, they are anyways going to produce 0 because they all are 0. What is decimal representation of this number? Here is a number which has all the leading bits as 0 except the last 2 bits. And second last bit is 1 and last bit is 0. So decimal equivalent of this number is 2. That is why we get the output as 2 when we print bitwise AND of 3 and 4. Let us now talk about bitwise OR operator. Bitwise OR operator, it produces the output as 1 when any of the input bits are 1. So we have two numbers x and y whose bitwise OR we want to find out. Please note that these operators are called bitwise, but they produce output as an integer only, right? They do internally bitwise operations and then consider the decimal value after doing the bitwise operation and then return that decimal value as a result. So 3 and 6, their binary representations are these and these, and when you do bitwise OR of x and y, let's see what do we get. 1 0 bitwise OR is going to be 1, 1 1 bitwise OR is going to be 1. Why is it 1? Because one of the bits is set. Here both are set, so 1. Here again one bit is set, so 1. For remaining bits, it's all going to be 0 because all the remaining bits, all the leading bits are 0. So our output is going to be a number which has last 3 bits as 1 and remaining leading bits as 0 0 0. Right? If it is a 32-bit representation, then these are 29 zeros. If it's a 64-bit representation, these are 61 zeros. But these are all zeros. Only the last 3 bits are set. So what is the decimal equivalent of this binary? This corresponds to 1, this corresponds to 2, this corresponds to 4. So 4 plus 2 plus 1, 7. That is why you get the output as 7 in this program for the second line. Let us now talk about our next bitwise operator, which is XOR operator. XOR operator produces the output 1 only when two input bits are different. So we are given the numbers as 3 and 6. These are their binary representations. When we do bitwise XOR, we produce the output as 1 only when they are different. So 1 and 0, they are different. So we produce the output as 1. 1 and 1, they are same. So our output is 0. 0 and 1, they are different. So our output is 1. Now if we consider the remaining leading bits, they are all 0 in both of them. So they are all going to be same in both of them. So we have a number in the result whose last 3 bits are 1 0 1 and remaining leading bits are all 0. If it's a 32-bit number, then these are 29 bits. If it's a 64-bit number, then these are 61 zeros. Now what is the decimal equivalent of this number? It's 1 plus 4, 5. So we get the output as 5 when we do bitwise XOR of x and y.